Hi, everyone. I'm Aaron Larson, executive editor of Power Magazine, and you're listening to the Power Podcast. On today's episode, I'm joined by Dr. Dario Gil, Undersecretary for Science at the U.S. Department of Energy and Director of the Genesis mission. Dr. Gil, thanks for joining me, and please tell a little bit about yourself and your background and what you do at DOE.
Sure thing, Aaron. It's a pleasure to be with you today, and thank you for the invitation. Yeah, so I came to the Department of Energy after 22 years at IBM, where when I left, I was a senior vice president at the director of IBM Research, where I was responsible for the research activities of IBM. And I spent my career focused on semiconductors, artificial intelligence, and quantum computing. And I took my current role at the end of September as last year. And, I'm a passionate person about science and engineering. I love everything that has to do with science and technology. And I'm just delighted to be on this role and to work with the national laboratories and the whole ecosystem that supports physical sciences research in America.
From what I understand, the Genesis mission aims to address several challenges, among them some challenges related to nuclear energy, which will be of interest to our audience, but also many other things. To kick off this discussion, can you give just kind of a high-level overview of the mission?
The Genesis mission has a very simple thesis that is that we are in the midst of a computing revolution that is going to transform the practice of science and engineering in America. And as a policy objective, we seek to double the productivity and impact of America's $1 trillion a year research and development engine within a decade. The way we're going to go about doing that is to do three things. The first thing is to build a platform to accelerate discovery. And this platform is going to be built on the triad of computing, namely the role of high precision, high performance computing, AI supercomputing, and quantum computing. And we will build in collaboration with the private sector and our university partners an agentic AI framework on top of that underlying infrastructure of high performance computing, AI, and quantum to allow for the acceleration of scientific workflows. So that's pillar number one, right? And think about it as looking at the world of AI supercomputing and so on as a new scientific instrument over time that allows us to see or operate with a level of sophistication and deal with complexity in ways we couldn't do before. As you pointed out already, pillar number two is the construction and execution of a portfolio of national challenges that exercise this new methodology of assisting our scientists and engineers with AI to problem solve faster than we could do before. And we have a portfolio of challenges spanning energy. You mentioned the nuclear one, but we also have on the energy domain projects on fusion, on the grid, etc. We have projects on discovery science, on the physical sciences, and we have projects on national security. And then the third pillar is to engage with universities to think about how the evolution of curriculums and degrees and experiences for students should evolve in the age of AI. What will it mean to be an electrical engineer or a mechanical engineer or a physicist and continue to deepen that profession, but also to leverage the advances in AI? So those are the three elements that constitute the Genesis mission. And it is led by the Department of Energy. It was launched the January before Thanksgiving of last year by the president. And it chartered the Department of Energy to lead that national effort, not alone, but to take a lead through the national laboratories working with industry and universities.
You mentioned fusion energy, which I'm personally very interested in. How do you see the Genesis mission helping to advance fusion technology?
Fusion obviously is like one of the most exciting endeavors that we could pursue, in the field of energy, but also in science and technology. And one of the capabilities that has been built by the community with the support of the Office of Science and the national laboratories has been to combine experimental efforts on fusion, right, where we have unique conditions where we create these plasmas, and there's a variety of, obviously, as we know, of fusion types. But there has been environments in which exquisite data has been created thanks to very unique instruments and platforms. And the community also built high performance computing simulation codes. And one of the wonderful accomplishments of the field of fusion has been that these high performance computing simulation codes really match the observations that we have with experiments, right? So we had discrete experimental efforts combined with high performance computing simulation codes, and they match really well. So now enter AI, and what is the opportunity we have to accelerate the path for fusion energy? With AI, we have the opportunity to create what is known as surrogate models. And what that means is that we can take the output of those simulation codes that, although very accurate, are computationally expensive. And to do, some of those simulations, sometimes they can take us days or weeks or even months, depending on the level of fidelity that we want to be able to obtain in a particular configuration of a plasma, as an example. And what you can do with a surrogate model is you take the output of the simulation and use that output to create a set of examples of a training data set with which to train a neural network running on an AI supercomputing stack to issue predictions. So the network, as we know in neural networks with the world of AI, you can issue predictions of what is anticipated. But in this case, the predictions, you're learning them through the training data sets that come from the calibrated physical models that run on the high performance computing environment. And the punchline on this is that the surrogate model can be 10,000 times faster than what we can obtain with the simulations in high performance computing. So now think about what that means. Now that we have these surrogate models that can run 10,000 times faster, now we can create, let's say, on a fusion reactor, we can actually create a model of that environment and optimize in an engineering fashion the different configurations, operating parameters, and so on by exploiting a model that runs 10,000 times faster. So now you can iterate in a matter of hours or even minutes sometimes, and that is going to transform our ability to design the next generation of fusion reactors and systems. So that's on the sort of design front, on the front end. But it's also been beautiful work that the community has done, and there's been examples of this, for example, with collaboration with Google DeepMind and Commonwealth Fusion and others, where you're using AI to optimize the operating parameters of the plasma of the reactor itself. So this is another dimension where AI is going to transform the stability of the environment and the power output that ultimately we're going to be able to get out of these systems.
Grid modernization and alleviating interconnection bottlenecks are some other items that I know the mission is focused on. How do you expect your team's work to impact the interconnection queue, for example, and other grid improvement projects?
Let me give you a couple of examples. Grid operators have told us, the Office of Electricity in the Department of Energy, that 80 to 90% of interconnection applications are deficient. So, 9 out of 10 projects that developers are planning to build new generators don't even get the application right when they're requesting to connect them to the grid. So, one area that there's a program in the Office of Electricity called Artificial Intelligence for Interconnection that aims to solve this bottleneck. And the idea is to work with industry partners and to deploy AI agents that actually help the submitter to get that pre-submission right. Like, so when there are corrections that are needed, so to proactively correct deficiencies and help them through that, through this AI agentic framework, such that when the final interconnection applications are submitted, they will identify any parts of the applications that may need fixing, and therefore is going to allow the utilities engineers to accelerate any kind of like corrective action processes that are required. And we estimate that if we could help improve this, we would expect the interconnection studies to begin up to a year before it would have been possible without those tools. So that's one example. Another one has to do with again, back to talking about simulation and how when our engineers in the industry need to calculate, for example, like grid expansion and interconnection scenarios. Let's say, for example, because of large data center loads. Today, based on the simulation environments and optimizations environments that we have, it's typically limited to like 1 to 2 location scenarios due to computational constraints of the existing power flow solvers. So one of the projects that is taking place at the Brookhaven National Laboratory is, a project called Grid FM. And Grid FM is an AI emulator that allows you to improve the amount of power flow calculations by a factor of 100x. So let me give you an example that the team is exploring that has to do with the Texas transmission grid, right? So in that calculation, there's 2,000 nodes and there's over 1,000 potential connection points. And they have to explore as part of this calculation 4,000 different contingencies. So if you went and try to approach this calculation and you have 10 different 24-hour load scenarios at 5-minute increments, you basically end up with something like 10 billion power flow simulations. And in today's method, it would take you 20 years to be able to do this scenario planning for the evolution of the Texas grid, right? With AI emulation, instead of 20 years, it's going to be done in 2 months of calculations. So again, it's just an example of how transformative it can be in allowing us to make a real world difference to our energy systems.
AI is increasingly being used to optimize and solve energy challenges, as you've mentioned, yet its rapid growth is also driving a surge in electricity demand through data centers, which it seems we're talking about every day here at Power Magazine. How do you reconcile the two forces when thinking about the net impact of AI on the energy system?
I mean, you could not be more right. It's like the arrows go in both direction, right? Is energy for AI and AI for energy, and so so let's unpack those two elements. Look, at this point, the rate limiting step of how fast AI can progress and the impact that it will have in all our lives is going to be dependent on energy, right? When I look at the appetite to build these AI data centers and put in towards productive use to improve the productivity, and problem solving, the scale of it when we're talking about, we used to be so impressed when we would build a supercomputer, for example, at the Department of Energy that would consume maybe, 30, 40, 50 megawatts, right? Now, in the last 4 or 5 years, now we're talking about computers and systems that are like a gigawatt, multiple gigawatts. There's projects to build data centers now that are 10 gigawatts. So I'm frankly, and I know all of us are still processing, right, just the scale of what we're discussing. So as a consequence of this, we have gone from a world in which, electricity demand for many decades in the United States was like flat to slightly declining to a world where we're going to need to add, hundreds of gigawatts of compute capacity to power the data centers of the future and reindustrialization and many other national objectives that we have. So, so we have our work cut out for us, and that means on the short term, there are things. What can we do to optimize the grid that we have and add more firm generation capacity? There are also, major initiatives that the administration is pursuing to allow data center operators to build their own generation behind the meter. Sort of like we're also investing very aggressively on driving a renaissance of nuclear, right? And how do we accelerate that and build it? And then we chatted a little bit about in the horizon beyond that. How do we bring the world of fusion into this equation, right? And then if you look at the AI component on its own right, one of the things we have to dramatically continue to do in the field is to improve the energy performance of these systems. And what that means is that we got to continue to improve architectures of the AI accelerators such that they are more and more power efficient over time. And there's a lot of optimization that is going to be possible. I mean, not to overly simplify, but just to give an intuition to people that, our brain that is, quite capable, right, of a broad ranges of intelligence and problem solving, we dissipate about 20 watts, right? So like a little over a light bulb, right? And if you look at like what these GPUs consume and these in these large centers, right, are so many orders of magnitude more consumption. So we know that biology tells us that it is possible to create intelligence, with a great degree of efficiency. So that's just to give an intuition that there's going to be a lot of architectural innovation and possibilities in the years and decades to come to continue to improve the efficiency with which we can do AI compute. So both will go hand in hand. Energy and AI are two sides of the coin.
And you mentioned how the scale of supercomputers has changed over time. And I understand there's a couple of new supercomputers being built at two of the labs. I think Argonne and Oak Ridge are both getting large computers added to their systems that are supposed to come online in the second quarter of 2026. Can you talk a little bit about those projects and what those supercomputers will enable within the Department of Energy?
Yeah, this is a very exciting element on the triad of the computing revolution that I was referring to at the beginning of our discussion. This is the second leg, right? We need to add more AI supercomputing capacity to the national laboratories and to the science ecosystem of America. And the way we're approaching this is also to work collaboratively with industry. So we form a Genesis consortium and we have 27 industrial partners in it. Among them include companies like NVIDIA and Oracle and AMD and HPE. And through that partnership, NVIDIA working with Oracle is standing up a cluster at Argonne National Laboratory in Illinois that is being, installed in the second quarter and will be operational this year to deploy a system with about 10,000 state-of-the-art GPUs, and then working with AMD and HPE at Oak Ridge National Laboratory in Tennessee, we're building also, a cluster, a significant size cluster with many thousands of GPUs as well. That also is going to be operational this year. Now, if we look even ahead in 2027, there's a project also underway with NVIDIA and Oracle to stand up a 100,000 GPU cluster in 2027 in Argonne, which would be the largest science-oriented cluster in the world. And so what's going to enable us to do is I was giving examples before of how do we take the incredible strengths we have in the national laboratories of unique data sets in the physical sciences? I mean, on fusion and on nuclear, on high energy physics, in biology, and you name it, and then use that and the simulation codes that we have built over many years and decades, and allow us to create these surrogate models that can run natively at 10,000x productivity and efficiency improvements with these AI supercomputers. It is also going to allow us to run frontier models and customize them for science. The great new frontier of AI, we've seen it over the last number of years that it does a really good job with language, with natural language. It does a good job with coding, right? With software programming. But the next frontier is get AI to do a great job also with physics and chemistry and materials and biology and engineering. And we need these AI supercomputers to help us train the next generation and customize the next generation of AI models to help us with our mission. So they're just going to be incredibly versatile scientific instruments to take us into the next frontier of science.
You mentioned partnerships with NVIDIA and Oracle and some other private companies. How do those public-private deals actually work when the incentive structures are different, such as between the labs and universities and private companies?
Yes, the philosophy in the Genesis Consortium is to reach out to stakeholders that are key to the R&D ecosystem of the United States. And the stakeholders are federal agencies, state governments, the private sector, universities, and philanthropies. And we are reaching out to each one of those stakeholders to ask them a fundamental question is, do you believe in this thesis that this computing revolution is going to transform science and engineering? And if you do, this is the flagship national science and technology initiative of the administration. It is the flagship science and technology initiative for the country at present. And we seek your help. We seek your help to co invest with us, to partner, and to bring your strengths to solve these problems together. And that's a philosophy with which we've approached those partnerships. And I got to tell you that the response from our industry partners, but so is true for universities and others, has been phenomenal. Examples I gave with, NVIDIA and AMD are just two examples, but I could list examples with other major companies where they're bringing their frontier AI models with new startups that have emerged to do AI for science. I mean, you have startups, small companies like Periodic Labs, and Radical AI, and the Prometheus project is a new startup that in which Jeff Bezos is the co-CEO on doing that. And it's been phenomenal to see companies large and small that already understand that AI is transforming engineering and science, and then they want to work with us. And the incentive alignment is that the national laboratories possess both the domain expertise in the physical sciences, unique scientific data sets, and unique user facilities and instruments. Like, when you think about big science projects in America, whether it's building particle accelerators or, X-ray sources or telescopes and so on, those have been national efforts of the communities of the national laboratories and universities for many decades, supported by federal investments. And those user facilities are simply not things that the private sector can build, right? And so this complementary, right? We have unique strengths in the federal government and national laboratories. The private sector has unique strengths. The universities have unique strengths. And the philosophy is let's all co-invest and join forces to solve these national science and technology challenges and to build a platform together.
Mm-hmm. The U.S. has engaged in flagship initiatives before, such as the Manhattan Project and Apollo. Yet those missions had specific goals, which, for example, were building an atomic bomb or going to the moon. You knew when you got to the outcome. In your case, what do you expect to achieve when this mission is done, or what will success look like?
Okay, so let me actually start with an example and then generalize it of what success looked like. And let me start with the problems first. And let me do it by telling you the story of perhaps the best known example of AI for science, which is the story of protein folding and AlphaFold. So in 1971, at Brookhaven National Laboratory, there was an effort that got started to create what became the protein data bank, that it was going to be the repository with which to store all known proteins. And proteins, of course, are the building block of life, right? Are fundamental to biology and has myriad of important applications, for health and so on. So at the time in 1971, they were using a synchrotron, and they would prepare a sample and they would illuminate the sample with X-rays. And the X-rays, as it went through the protein that was in the sample, they would, generate a diffraction pattern. And then from that diffraction pattern, you would reconstruct the three-dimensional structure of the protein. And when they launched it, they had 7 proteins. So, long story short, it took 50 years of effort by the community, right? Of excruciating experimental efforts, simulation code, software development, and so on, to build a database that had 200,000 proteins, the three-dimensional structure of proteins, after 50 years of effort. Now, the Google DeepMind team used modern AI techniques based on deep learning and so on to leverage that data set to train this neural network to, given an amino acid string, predict the three-dimensional structure of from this neural network that was trained with the 200,000 proteins that had been characterized after 50 years of effort. And we went from 200,000 proteins to 200 million all known proteins in 2 years. So think about it, 50 years to do 200,000, then in 2 years, 200 million. So one success criteria to answer your question will be that 3 years from now or 5 years from now, we have 50 to 100 AlphaFold examples across all domains of science, right? And so that will be one measure of success, that we have area after area where we see both an outcome in terms of scientific discovery or time to solution or cost of it that is transformative. Number one. Second, that in the demonstration of that portfolio of acceleration of science and impact on important problems that we care about, we also have left behind this platform to accelerate discovery. And what that means is that the scientific community of the United States has the AI supercomputing capability and the next generation of quantum computers to be able to help them do science better. It would all success also would mean that just like now we can say that AI does coding well and language, that AI is fantastic at helping us do physics and mathematics and chemistry and biology. Those are quantitative things. Do we have AI supercomputers available to the scientific community and the national laboratories? Is AI capable of doing science and engineering and helping us with that? Do we have 100 AlphaFold stories around this? And then have we evolved our curriculums such that now every physicist or engineer that graduates is equally fluent in their domain and in the application of these unique new capabilities to their profession? Right? So those are all the things that we can be, very quantitative about. And perhaps I'll leave you with the thought of, sometimes a platform can sound kind of abstract, but, I also give the analogy of imagine that it was the 1970s. And we were starting this project to connect a few computers with each other with a new protocol, right, with TCP/IP. And at the beginning, you looked at it and you're like, well, that sounds kind of arcane and in the weeds. But later, you came to recognize that what we were building is the internet. And now we come to appreciate that the internet doesn't solve one thing. The internet is a platform, it's a building block that has transformed the nature of our world. So think about this, about also kind of like an internet of science, where we seek to connect all the scientific instruments of our national laboratories and our university ecosystem with an intelligence layer that allows us to execute enormously complex scientific workflows, much in the same way that we don't give it a second thought that we could have in this podcast discussion, and we're all sitting in different environments with different kinds of computers, and it all works seamlessly. Imagine an internet of science that has been made possible by the Genesis mission.
My last question deals with your transition to the DOE. And, you went from running IBM Research, which is one of the premier corporate labs, to leading this government initiative that involves coordinating 17 national labs and 40,000 scientists. What's the biggest difference there's been for you going from that private sector to the DOE?
My absolute favorite part of the Department of Energy and the national labs is the strong sense of mission that everybody here, both the federal employees and our partners at the labs, have. I've come to, really enormously value and appreciate, and it just resonates so strongly with my temperament and my passion that everybody I interact with is driven by purpose and mission, and the mission of delivering, affordable, reliable, and secure energy to America, the mission of discovery in the physical sciences, and the national security mission of the National Nuclear Security Administration and everything that we do in the Department of Energy. So that is my absolute favorite part. Like there is not, I don't encounter anybody that approaches their work with cynicism or pessimism. They are passionate about solving these missions on behalf of their fellow citizens. My absolute favorite part. Mm-hmm. And but then there's all other things that are also in common. Where my experience in IBM has helped me. I spent my whole career in the field of research and in science, and I just love scientists and engineers and the work that we do. I had the fortune, even when I was at IBM, of serving on the President's Council of Science and Technology Advisors and in the National Science Board that oversaw the National Science Foundation. So I've been for many years involved in science and technology policy matters in the United States. But the opportunity to now do this full time and be able to serve and give back to the country that has given me so much, but also in this moment where, as we discussed today, there's such consequence and there's so much transformational change that is happening in the field of science and technology. I just think it was like a unique moment that I am just, it's the privilege of my life to be able to do this and to serve with my colleagues here at DOE.
All right. Well, Dr. Gil, I appreciate the work that you're doing. And again, for listeners, I've been speaking with Dr. Dario Gil, Undersecretary for Science at the U.S. Department of Energy and Director of the Genesis mission, which is an amazing mission that's going on right now. So thank you for your work. And is there any last words you'd like to leave the audience with?
That we ain't seen nothing yet. And thank you for hosting me today.